So yeah, I hope you can hear me. Okay, so let us continue with where we left last time. So it's F divergence, how it's connected to MLE. Actually, we have done this already, and we will do GANs. We will try to complete GAN today, derive the generic form of GAN, and we also look at the basic Python code. So these are the things. So basically, today we will do GAN, and this motivation stuff we already did. Why we use KL divergence, right? So we have seen this derivation in the last class, that if you see KL divergence, then this is our KL divergence, and P is the distribution that we want to learn, and P theta is the one that we are learning. Okay, so P is the real one, and P theta is the one that we are trying to learn. We assume that this is some parametric distribution, and so what we did as a trick is that we introduced the entropy term. So basically nothing changed here. D here remains the same. We did this additional trick that we introduced the entropy term. All this derivation we have done, so we have to actually go through this quickly. So effect of all this, you can check the previous slide. Effect of all this is that I can write this as an expectation, and eventually, since even Px has nothing to do with theta, and this is argmax with theta, so essentially we can get rid of the P as well. So now, as you can see, it is nothing but maximum of the log likelihood. Okay, and this is exactly what log likelihood means, where we take some parametric distribution P and X. Okay, it may be a vector of random variable, so it may look like a joint PDF, but this is what log means. So there is a log also there, so that's why we will call it log likelihood. So all this is what I described again, is the same thing. You can follow up with the previous, and then this is also we have done previously. So why KL being equal to MLE is a good thing? Well, there are a few properties of KL divergence itself. The non-negativity, and it's zero only if P theta is equal to P. So kind of you can use that as a guiding principle, or the loss, let's say. So KLE is equivalent to MLE, that was proved in the last slide, and then MLE estimator is a consistent one. So we have seen this in the statistical inference, that that an estimator is a consistent one if on average the sample average. So in this case it's the sample mean. This is sample mean of the log likelihood here, which if it goes to the true mean. Okay, as n tends to infinity. So that's how the consistent estimators are defined, and same thing we can do for the reverse KL. Okay, so we have seen KL and reverse KL are not the same if you flip P and Q. Okay, so all this we have done. Then if KL is MLE and MLE is consistent, then why don't we continue to use MLE? So again, we have already seen in previous lectures that the main thing when we are going to do the MLE estimate is indeed this joint PDF, because xi could be a vector of random variables. So in this case, it's xi is the ith sample, let's say, and each of these are components of xi are themselves some random variable, right? So essentially, for higher dimensional problem, if I take an image which is my ith sample, this image has pixel entries, and each of these is a random variable. So you can think of such a big xi there. So the whole problem is how do you really look into this P theta xi, which is a joint PDF. Okay, so that's what I have written here as well. Xi being coming from a real distribution, which could be xi could be some cat image, and n could be the let's say grayscale image, then MNIST, then 28 by 28, or CFAR, then, and so on. So basically this n grows quite big. P theta xi is a joint PDF, as I just said, and you cannot just use independence assumptions on these pixels, because as I have been repeating this time and again, that the reason why you see cat images is because they have certain dependencies that create features for a cat and so on. So complete independence assumption and breaking this into joint PDF into product of individual PDF is not a good idea. We have done this quite a lot. So how does F divergence help? So this is the main thing for today's class. It will help in obtaining a tractable lower bounds. Okay, so basically you have seen KL divergence. KL divergence is MLE estimate, but again MLE itself is not tractable, right? So overall the way we stand is things are not tractable. Okay, so we go via a different route where we use F divergence, and that's That's where some maths help. So, so what it will lead us to, we will prove this. So what it will lead us to is that the KL divergence, as you can, not KL, or let's say the F divergence, because now we have the F term here. So this F divergence is lower bounded by some term we see there. Okay, we have to make sense of that term, but for the moment, you may say that you have some kind of a lower bound. You still have to interpret that, but this is what is our plan today. Is KL divergence as such not regular, but we want some lower bound which is a good lower bound, okay, which goes closer to the KL divergence. So that is, we would settle for a good lower bound, okay. So that's our plan, and that is why we need some maths. And the maths that we need is something borrowed from the convex analysis. And as you can see here, we are trying to recall something called convex conjugate. So F star T is a convex conjugate. It's defined to be supremum over x of tx minus fx, where fx is a given function. Okay, so someone gives you a function fx, then f star is called the conjugate if you can solve for that supremum problem. So we have done some practice in previous classes, and this is this f star that you see showing up in this lower bound here. Okay, so this is that f star that somehow shows up here. So that's how things are kind of related. We still have to figure out how this t came and how we have this f star of t, and then things are getting subtracted. Okay, so this is the idea proposed in this paper. You can have a look at this, and this is the FGAN paper, and we are kind of going to derive what was mentioned in the paper. Okay, so in F divergence, F, if we assume to be closed and convex. So convex, we have seen its convex function is like a ball shaped, and closed function being closed means that the epigraph is a closed set. Okay, so we also know what is a closed set. Okay, so so then we know this reflexive property of the conjugate gradient. I have mentioned this in the convex analysis, and without proving this. So if F is closed and convex, then the conjugate of the F is F itself. In other words, F star star becomes F. Okay, so that's also something. If you want to have more reference on this, you can look at the Boyd's book. So then we have this property. That's what we are looking for. F star star. Okay, so if I did it, if I look at the F star, then F star of star, then essentially I'm looking for conjugate of F star. Okay, so it's like supremum of tx. In place of f, I put f star. So then I have f star star. Okay, and what this result says that if f or your original f was closed and convex, then it will be f star star will be nothing but your original f itself. Okay, so this is the reflexive property that we are going to use, and this is essentially the main thing. And you can see the last term expression is what we saw in the beginning. It serves as a lower bound. So let us see this. This is a simple derivation. So we have on the left is F divergence, and then we have in the F divergence we have Q, and then we have some F of, if you recall the definition on F divergence, then we have Q, F of P over Q. Okay, so here essentially we would had F of P over Q. So I go there, and in the F, in place of X, I substitute P over Q. Okay, and then I use this fact, and I go here and I use that X, which is P over Q, and wherever I have X, I put P over Q here. So that's why I have T in place of X, I have P over Q minus F star T dx. Okay, so that's what we did here. So overall here, if you see the soup term, it was some Fx. Okay, but then and in the F divergence case, that x was P over Q. Okay, so that's what we did. We used the reflexive property, and we put this supremum here. Okay, and the reason why we may do that is that it is giving you some variational form. Okay, variational form here means that that instead of the usual F, now you have some optimization problem inside. You may not solve this optimization problem precisely, but you may get into something which is a lower bound kind of thing. Okay, so that's how. So sometimes what happens is, rather than working with the exact expressions, that's how you try to bring in some inexactness, but which is tractable. Okay, the whole idea behind bringing this guy inside is that now it's giving me some variations to try with different t, and it may not be the optimal t where it achieves the supremum, but it gives me some hold of something to play with, okay, rather than just saying it's f of something. Okay, so then some more advanced tricks are used. I mean, just one big trick is used. So if you see here, q can go inside. Okay, because q does not depend on the t, so supremum will not really do anything for that. You can easily put the q inside, and q gets cancelled. So here this q and q gets cancelled, and qx gets multiplied with f star t. So this is what we did. So until here it's fine. Now this is the big trick. This is the main trick here, where again advanced analysis concepts are used. So the idea here is, when can you bring the pointwise supremum that is going on inside the integral, and you can move it outside. Okay, so so there is a result from advanced calculus, which we won't like to go into much detail, but there is a pointer. I will point to that paper. So when it's possible to bring supremum from inside to outside. In my previous video lecture on YouTube, I explained this again intuitively without proving this in detail. You may also have an intuition behind this from there. So if you indeed want to bring this supremum outside, then you must replace t by some operator. Okay, so earlier if you see the t that is there, it's more like a pointwise supremum you are going to take. So some t is there, okay, and you will check whether it's maximum or not. You will go for some other t or not, but then and inside you have this pointwise max, and then you're looking for area under the integral, right? So this is what it means. Here it means that the first step is to actually know what is the supremum of this guy, and then calculate the area under x. Here it's now a bit different. Here it's saying that what are the can there exist an operator t, okay, which I can replace the small t by the capital T, and this area that I'm getting now, if I can supremize over that operator itself t. Okay, so this is the main thing here, that there is such result where we can do that. Okay, so essentially this is the main trick here. So for practical reasons, you can remember these things. Okay, when we have supremum, and this could be like generalized. You can see that the thing to learn here is that wherever t is there, it could be some other expression in t. Okay, so in this case it's tpx and f star t, something like that. But the thing to memorize here is that some expression is t in there, and there is a supremum inside the integral, and if I'm supposed to take it out, wherever t is there, I replace it by the operator t. Okay, so as long as you can do that, you may perhaps use this result in other areas you may encounter. So this is what we did here. So that is essentially the main trick. Now use the linearity of the integral, split this integral and this integral. So the first integral, if you see, this is with px, right? So this is like expectation with px of tx. Right, and here we see qx. So this is and both px and qx are PDF, obviously. So the second term is like expectation with respect to qx. So that's how we write expectation of x from q, and this is f star tx, and then here we have px taken out. So this is expectation of, I mean not taken out. It's the expectation with respect to PDF. So this is x follows p and tx. So this is somewhat related to what we wanted to do. So we were looking for this lower bound, if you can recall, and since we have the supremum, if you relax the supremum, then certainly you get the lower bound. So here the point here is that you won't be able to in practice solve perhaps the exact supremum problem. So what happens now is that if you take any arbitrary t, that will give you a lower bound of this. Okay, so any arbitrary t will be going to be less than equal to the supremum, because supremum is supremum, right? So it is the biggest value you can have. So this essentially gives you the, once again, so this essentially gives you, so I have just copied that expression again here. So since we have supremum, any arbitrary choice of tx gives us a lower bound. Okay, you could take some other arbitrary t, it will be some other lower bound, but as we know, supremum is the least of all the upper bound, right? So idea one, assuming that you got this, right? So from here, so the first step we see is what is our t, right? So we can parameterize t. We can say, okay, I don't really know what is t. Let me use a parametric function t phi, okay, where phi is some parameter. So that's the idea number one. And if we do that, then we can replace wherever I have t, I replace it by t phi and t phi, okay. And idea here is that I want to supremize over the t phi, okay. And actually I have also jumped up and did one more idea, which is idea number 2. And if you can see here, now the x that is being generated, what we are saying here is that let this x that I see here, which is being generated here, let it follow from the p theta, that the distribution that parametric distribution that I want to learn, okay. So this is your original template, and how you are going to kind of modify it for generative model, this is what we are trying to do, okay. So far what we see here is some math result, but then so we may say that x follows p is some real distribution, x follow q, let me change q by p theta, that's the parametric distribution that I'm trying to learn. And one more step is that this x that I generate, I see this as coming from some push forward distribution. So in other words, I will generate some z which is from a non-distribution, and I have a generator g theta which will map, which will take z to some sample that I'm looking for. So there is this push forward distribution going on here that we defined earlier in the class. So in fact in generative modeling this is how we define, right? From a non-distribution where I can sample, it should go to a distribution that I want to generate, okay? So we have done 2 ideas here. First thing is t, parameterize the t, because in general we don't know what is optimal value, so let it learn from some supervised learning, okay. And the second one is replace q with the distribution that we want to learn. So indeed here it's seen as some push forward distribution. So ultimately the domain z is some known distributions you can sample from, some standard normal or uniform, whatever. It's easier to do. You can do this in Python code. And then there is a map g theta that tries to generate something, and then there is this t phi, there is this another map. So we have to kind of bring in the discriminator also. So far what we understand is we have 2 parameterizations now, one for the t and one for the theta, one for the generated image, okay, from the known sample. Okay, so this is exactly what we did. So we can now the remaining thing is the f. So we have derived these results in a very generic form, right? So we became with f divergence, and we know that KL divergence was a special case of f divergence when we take x log x. So if you take f equals to x log x, I believe you exactly get KL divergence, okay. So f, one possibility is that so this gives you research problem also, okay. So this thing essentially also gives you some research, at least let us say to start with, what could be interesting f to choose, okay. So KL divergence is just one case. Now f could be any convex function that we have seen, okay. Let's say closed and convex, and then you may go in this direction and do further research with it, because there are so many convex functions around, okay. Maybe there's one of these will be better than the existing state of the art, okay. So in the Goodfellow GAN, so what they propose is something like this. So there are 2 assignments that I leave it up to you. These are simple, very simple assignment problems. So and we will use this, okay, to make a very one possibility for a GAN, which was the original GAN architecture. So basically it's all about f now, okay. So what f I will choose so that I will get the original GAN. So let us choose one f to be like this, okay. So x log x minus x plus 1 log x plus 1. Then so that the f divergence will be this, okay, where this is JSD is Jensen-Shannon divergence that I have also described in previous class, which is a symmetrized form of KL divergence. So you can see here DKL, which is KL divergence, so PP plus Q by Q, and then Q P plus Q by Q. So this is kind of symmetric variant of KL divergence. So this is JSD. JSD is given to you in terms of KL. KL is something you know, and now you have to prove that with this choice of f, your f divergence is exactly like this. So this is a simple derivation, okay. You just put in you start with the f divergence term, and in the place of f you put x log as this, and thus rearrange the terms, and it indeed comes out to be like this. Minus log 4 will show up when we will look into the optimality and so on. So minus log 4 is interesting because it will shift the lower bound to be greater than or equal to 0 and so on. So we will see that role a bit later. So this is something you can prove as an assignment, and then we can save some time. And then so that the convex conjugate of f is that. So given that f is x log x minus x plus 1 log x plus 1, you're supposed to prove that the conjugate of that is minus log 1 minus et. So we have done some practice of conjugates. So you may try a hand on this. All these are interesting problems. So it's better that you enjoy doing it yourself. So and these are the two things. So what was missing from our previous derivation was what could be the f. Okay, and more or less we are thinking it will be some kind of a discriminator network, some kind of generator network, and then the missing piece seems to be the f guy. And one possibility, if you want to derive the original GAN architecture, then take this as an f. So that's why I said different choices of f will give you some interesting ideas to explore. Okay, so this is actually could be a research problem now. Okay, so assuming that you have done the assignment, and for fx you found the f star, and then we take now the third one is something that we just take t phi to be log of some log of d phi x. Okay, so let us make one more assumption for the operator t phi to be of the form log of d phi x. Okay, so with these choices, all three ingredient, and Z usually is reserved for samples coming from standard normal, right? So this is kind of a standard notation. Z is sometimes, just by looking at Z, you know it must be kind of standard normal, right? So it's so used so frequently. Okay, so our original optimization problem, we left it here, right? So we left it there, and we were wondering about f, and we were wondering what could be t phi as well. So we did two things. So we choose the f to be like this, and then what we really need is f star. So we had this minus log 1 minus et. So we put that 1 minus log, and that gets cancelled because we have exponential here. So e to the t and t contains log. So log and e gets cancelled. So you have this 1 minus d phi g theta z here. And this was the very simple term. T phi was taken to be log d phi from here. T phi was taken to be log d phi. So that's, we keep it as it is. So approaching towards again, this is our current setup where we want to have this min-max problem to solve here, right? So okay, so essentially this defines the GAN architecture, and G could be, G is your generator, D is your discriminator, and so as you can see from the nature of this loss function, it looks like a classifier loss. Okay, so log choice was kind of meant for that. Okay, so so if you see the algorithm, now we have a full algorithm, and you change the notation slightly. So in place of d phi, now you call it capital D. In place of g theta, now you call g. Obviously, g has its own parameter, so we are not indicating those parameters right now. We call g itself as some parameter. Okay, so there is a vagueness in the notation here. So keeping those aside, so g is some parametric neural network, d is some parametric neural network, and this is the loss function used in the original GAN paper, and this is the algorithm that we have. So let us look into algorithm now. So this algorithm says, this is taken exactly from the original GAN paper. So it says mini batch stochastic gradient descent training of generative adversarial networks. The number of steps to apply for the discriminator is k, is a hyperparameter. We use k equals to 1, the least expensive option in our experiment. Okay, that's fine. So let us see this. For number of training iterations, do. Okay, so this number of training iteration is something you decide, obviously. And then for k steps, so as it happens, k is taken to be 1. So perhaps they took k 1. So this for loop will run just once. What it says is that sample mini batch. Why are you doing sampling, right? You're doing sampling because here there is an expectation, here there is an expectation, right? So expectation means the average, right? So what you're trying to do is that what is the average of the log dx, right? And so real expectation, obviously you don't know, so you will go with the sample mean, right? So we have seen in the previous statistical inference that the true mean in reality we approximated via sample mean. So what you see here is a sample mean, right? So these values are calculated for samples and then divided by the number of samples. So this is exactly what sample mean means, right? So this is what we are doing. We sample mini batch of m noise samples. So we have created m noise samples. Remember, Z is some noise, right? So noise here means something taken from from let's say some known distribution which usually is standard normal. So we call that noise. Okay. So there are mz of these from a noise prior PG. Okay, so in this case again you should fix those notations. So here in the actual algorithm they call it PG. Okay, so here we may use that. Okay. Right. So and then we have a sample mean of m examples. So here example means the real figures. Okay, the real images, let's say. Okay. So these xi's are let's say m cat images you have. And p data here refers to the real distribution data. Obviously, these samples that I'm taking are actually coming from the real data, okay? Because those are real cat images, and these guys are the noisy ones. Now update the discriminator by ascending its stochastic gradient, right? Why do we ascend? Ascend because it and this is for the discriminator, right? So we ascend because it's max of d, right? So this is max of d, so you have to do a stochastic gradient ascent because you want to maximize the value, right? So you do plus gradient direction, right? So we have this sample mean corresponding to this, and then because if you see for the discriminator, it depends on both terms, right? Because there is a d here and there is a d here. So that's why you see log d here, log d here, and so it is being computed over xi, zi's, and all this, right? So this whole term, expectation term needs to be computed. Sorry about that. So you could have done. So you could have done separately also because you see expectations separately, but it doesn't matter. You can combine them as well because both are being done for m. Okay, so that is for the maximizing the discriminator, right? So that's what we are doing for maximizing the discriminator. Here you can see quietly this parameter for the discriminator is introduced, this theta d, right? So theta d are the neural network weights for the discriminator neural network. Okay, so you are taking gradient of the sample mean of these guys, right? So it's kind of an approximation of the true mean, obviously, and you are supposed to take the gradient with respect to the, obviously you are maximizing the discriminator network, so you have to compute gradient with respect to the discriminator weight parameters, which are theta d. And now you can go ahead and do similar thing for the generator. So generator, if you see, generator is only lying in the second term, right? And so essentially, I just have to look because the loss will be independent of this. So because if you want to take a gradient with respect to the generator, this guy has nothing to do with generator because the weights of the discriminator are different from the weights from the generator. So that's why this guy is anyway going to get cancelled because partial derivative with the weights of the generator, this will be constant. So that's why you should forget this term now because the generator weights are only lying here, and you're supposed to do gradient with respect to theta g. So again we have expectation. So I need couple of samples to approximate this expectation term via sample mean. So okay, so we have done the sample mean, and in this case it so happens that I only need the noisy vectors, which is the zi. So this term sample mean is being computed over only the noisy vector. Okay, and then you're supposed to take the gradient. They have not shown the full gradient descent step. They just said update the generator by descending a stochastic gradient. So what you really have to do here is theta g minus theta. So I don't know if I have the. So here what you really have to do is theta g equals to theta g minus this. This is the stochastic gradient descent, right? So theta g is equal to theta g, it's a descent, right? So they go to the negative gradient descent. So theta g equal to theta g minus what the loss function here is a sample mean of the expectation here. So that's what it's going on here. And for the previous one, it's theta d goes to theta d plus, because it's ascent, right? So theta d is theta d plus of the gradient. Okay, so this is what they mean actually. Okay, when they say update. Okay. So okay, so that's how you are learning. Your discriminator weights are getting updated. Your generator weights are getting updated, and so on. At some point, you may be happy with this. One way to check would be like how the loss is behaving, where it's going to converge, things like that. There is a little bit of theory to know what is a good loss value, right? So when should you stop? Okay, so we may look into this a bit later, but essentially what goes on in training for GAN is that you run these two loops. Okay, so as such the algorithm is quite simple, but going via F divergence, we created more opportunities of possible research that you may try in future. Okay, so most book will just say this. Okay, okay. So I guess this is the main algorithm. We will come back to the theory part, like what is the optimal value of the discriminator loss or the generator loss. So we may prove that why this loss is good. We may quickly go through the GAN PyTorch. So this is how you may want to code these things. So these are the usual PyTorch routine. Most of you are quite familiar with this already. You call this this neural network objects and transforms, optimizers, dataset objects, some utilities for input output, NumPy for plotting utilities, for saving images, data loader, and so on. Okay, so I will not go into too much of these things because usually you learn these things on your own rather quickly. So I will just go very quickly with these things. So in the code, you will usually go with the batch size, like how many images you want to take in one go, and then how many epochs you want to do. So epoch usually in training means like one full sweep of the images, the data that you got. You want to go for the full sweep of that, and that so then you have to do 200 of this full sweeps through the data, and then you have sample size. Okay, so what would be how many sample sizes you are going to take. NZ here refers to the latent vector. So this will actually turn out to be, in this case, the noisy vector length. So your noisy vector length does not have to be same as the real vector length. So that's what it's about here. So k equals to 1. K equals to k is the same as the k that we saw in the algorithm. So this is like how many times you are going to run the discriminator loop. So these are some of these details. You can have a look into these things. Yeah, I guess. And then the last line is like about the device. So where you are going to run this code. So SCUDA here essentially refers to GPU. So if you have GPU available, usually GPU is faster, then you go for GPU. If not, then it will take the CPU. And I guess, yeah, so. And then it's about data loading. So how will you load the data? What is the folder? And some booleans, whether you want to train on this data, whether it's supposed to be downloaded, and so on, and which type of transforms you are going to do. So then you can define this method here, train loader, with the train data, batch size, and whether you want to do shuffling of the data. Usually when you take the batch of the data to train, usually you want to do random shuffling, okay, to break. Sometimes there is a symmetry that you don't want to have in the data. Then you may then you may convert the image to the tensor form, and then you may normalize this. Usually normalization is a good idea. And then you may convert this to some PIL image here. Actually, it's for creating the whole GIF file that you may want to see the full animation of how images started from random, and then at the 200 epoch, how it looks like. Okay, so these are things that you are pretty good at by yourself. Just for formality, I'm going through these things. And then we have this generator class here, and in generator class we have the initializer with the NZ here, and it is a sequential container that we are trying to use here. That means that it will go through this in a sequence. So first is the linear layer of size, input size NZ, output size 256. Then we use leaky ReLU. So leaky ReLU is an activation function. Okay, and 0.2 tells you how, because the slope can be defined by yourself, so you can give some prescribed slope, and then followed by similarly a linear layer, 256 input, 512 output, followed by leaky ReLU, 0.2 slope, linear again. It should match with the output, right? So 512, it's captured as an input here, and then the output is 1024, and then the leaky ReLU. So this is how neural networks are, right? So neural networks are powerful, but they look very simple, right? One after the others is just do linear and activation, and then finally 1024 input, and then 784 output. 784 suggests something, right? So it's MNIST, right? So the usual MNIST is 28 by 28 that you can also see from here. So 28 times 28 it will be, I believe, 784. We can check that. And so that is the output. The generator should actually produce the same size, ideally, right? Ideally, so same size as the real data size. So real data size was, let's say, MNIST 28 by 28. So finally we tell the generator that produce the image of the same size, like 784, and followed by 10H activation. So that's pretty much for the generator. Generator will take a random so the input to the generator is the random noise that we know, right? So from theory that we know that it will generate some random sample from standard normal, and that is of size nz. So that's what the random vector went in with size of nz. Remember, random vector size does not have to be the real vector size. That's what we're trying to stress here. So nz was 100 something, I forgot, and then internally it gets embedded or interpolated, whatever you want to say. From small size it can go to big size, then again go to small size, so it doesn't matter, but final output should be 784, which is the real image size. Okay, so this is how generator looks like. As you can see, these things are pretty simple. Now you can go to the discriminator. And discriminator is more like a classifier, right? So the output is sigmoid, and we have seen in the neural network class that sigmoid could be used in classification problem. It gives you some like kind of 0 and 1 values, so that could be treated as probability of outcome of certain input, right? So so here again, the discriminator actually takes the real image because it has to work with that. So discriminator is will take either the real image from the real data, or it may take data from the generator. Okay, so for the real image that is taking from the real data, obviously we know that it's a good one, but the one that it takes from generator, that we call it a fake data, right? So obviously generator is forced to learn in this way. So so here again we use the sequential container. We have linear and then Lecture-06 and so on. We are also using a kind of dropout. So this is also I mentioned in the neural network class that that dropout means that we may drop off some edges or some neurons or some perceptrons from our neural network. So what could be the dropout rate is something you can actually describe by this fraction of the dropout that you want to do. Then followed by linear Lecture-06 dropout. So there are quite a few dropouts being done here, and finally you have the sigmoid, and as you can see, the output just before the sigmoid is one number. Okay, so that's essentially the final output, and then it works on the sigmoid to produce the final probability between 0 and 1. Okay, regardless of whatever that output was, it may not be between 0 and 1, but after applying anything to sigmoid, it scales it to 0 and 1. So that's it. Your generator is created. So you can take the generator object from here by calling this here, and then you can get the discriminator, and whatever device is suitable. It's whether it's CPU or GPU that we have seen before, and just for check, you can print all this, and then when using, so we have seen ascent and descent routines, right? So for rather than using the usual gradient descent or gradient ascent, you may want to use let's say the Adam optimizer. Okay, so which is better than the usual gradient descent. So for both generator optimizer is Adam, discriminator optimizer is Adam. So optim is the is the tool we imported. So now we can use that, and then the loss function we are using is the BCE loss, binary cross entropy, for the discriminator, because it's like a classifier. It is telling me whether something is real or fake, right? So it's a binary thing. Okay, so we can define some arrays that captures these loss values for the generator and the discriminator, and also the images that you are that the generator is producing. So we can use these array, and then we can create real labels, we can create fake labels, and then we create the method for creating noise vectors, which is like a standard normal, let's say, and then some utility to save the generated image, and then the training module for the discriminator is like this. So basically here we have the discriminator and taking the real data, output real, and then with the output real we have defined the loss real, and then similarly for the fake data we have the output, we store it as output fake, and then output goes with the fake label, and then we have the loss fake here. So during the discriminator training, obviously we will do this backward backprop, right, on the loss real and then the loss fake, and then basically then we go to the optimizer step to update the weights of the discriminator, and then we add the losses that we observe for the real and the fake. Okay, so this is the discriminator training, and similarly we can do the generator training. So So discriminator training, as you have seen here, we have to do it separately, and this was similar to what the algorithm actually proposed. We have to do this loss two of these losses, right? So I have to go back all the way here. So this is what we have here, right? So here, if you see again, one second. So here, if you see here, this guy is working with the real data, right? So because this is xi, so this loss is the first loss. We call it real loss, and this loss is kind of like a fake loss because this is working on what is generated by the generator. And so generator, will be learning in the process, obviously. So it is working on some random noise. Initially, it will not really learn anything. So these guys, we call it fake. Okay, so this goes for the fake loss and this goes for the real loss. Okay, so that's why discriminator had these two terms there in the code. So let us go there. So here, okay, so we had these two losses, loss real, loss fake. Now, and so basically here it means like we could have done backprop for each of the terms separately, because gradient also we can do separately and kind of like add these losses. So, and then finally we have the train generator, and generator will only work with the yeah. So we initialize the optimizer with the zero gradients, and then output is from the discriminator, and then loss is between output and the real level, and then loss we do the backprop for that, and then we do the optimizer step to update the weights of the generator. So right. So that's how it is meant to be, right? Because discriminator was d of 1 minus log of the generator was there, right? So that's why you see this output is essentially finally coming from the discriminator, even for the generator loss there, okay? Because eventually it was d of 1 minus log of g of that, right? So so again, you do this optimizer step, and you update the weights of the generator, and the way you will, so these are just the modules, and then you will invoke these modules. So you will build these noise vectors, and then you run this full training module. So this is the number of epochs. In this case, it's like 200 here. I initialize the loss of g and d to be 0, 0. And for all the data in the train loader, with the way you have defined the batch sizes and all this is taken care of here. And then so the images and all these are taken care of here. Batch sizes are taken care of. And then this is the k for the discriminator, right? So this is the for loop for the k. And then you are creating this loss, and you are calling the train discriminator, and you are appending these losses for the discriminator here. Similarly, you are calling this for the generator, which is outside the for loop, obviously. So the first k loop is for the discriminator, and then you do this for the generator as here. Okay, so then you look at the generated image that is produced by the generator. Okay, again I'm hand wavy a little bit. You may go and do this by yourself. So we will put this as an assignment. So, and then where is this, like images are being saved, so you can save this and so on. Okay, so I'm not going into all this. So basically images will be saved after training, and you can plot this. So let us look into, so these are plotting routines and so on. So once the code is written, you can run this like this, Python vanilla GAN and so on. So when you run this, then it will show results like this. So you will have epoch 0 of 200 and so on. So then it shows, it prints the generator loss, and then it prints the discriminator loss. Okay, and then it goes to the second epoch, and then it shows generator loss, discriminator loss, and so on. Obviously, it will end at 200, and then it will print like done training. And this is how if you plot these losses for the generator, it's the red one, and then so you will see that they are going somewhere, right? So that is the interesting one. That will come from the theory, like where will they go, right? And when do you know when to stop? So here you will see they are going somewhere. Okay, it looks like just above 1, but we will see where they go. So initially the discriminator is going from below, and then somehow they're tending somewhere. So the code is taken from this reference. So you can go and just run these codes by yourself. And this is how the images will look like. So initially you will, because you are working with batches, right? So this, each of these is the Z vector you may think of. So it could, so each of these guys you may think of as some noise vector, right? So in our case we call it noise, and so if you plot the noise, obviously it will look like a noise vector, and then at 100th epoch it starts learning to generate the handwritten digits, okay? And apparently it improves at the 200. So you may say that it may not be still the best, so you may continue to train this longer, obviously, but clearly we see a couple of numbers which are looking like handwritten digits. So it has tried to learn the distribution of handwritten digits, okay? And what it is generating is not necessarily what exactly it saw in the training data. That's the point. It learned the distribution rather than memorized the training data, okay? That's the point of generative modeling. That's how you are creative, right? So the 3 that you see here may not be exactly the 3 that was seen in the training data, okay? But it learned the features of 3, okay? How 3 usually looks like. So again, there is a Colab notebook. So Colab here means that essentially it runs on Google servers. Your laptop won't be engaged at all. You can keep doing some other things while it's training on Colab, and you have option to use GPU there, okay? So this is a very good tool, Colab, for even initial research, okay? So you may play around with these things. Okay, so what we will do now is look into a little bit of theory of optimality of the GANs, okay? So let us see. So first theorem says for a fixed G, if I keep the G fixed, we know that it's a min-max problem, right? So max is going on with the discriminator, is trying to increase its score, right? So the score here for discriminator means that it's kind of like trying to learn better and better distributions, right? So, and then a generator is trying to minimize its loss, okay? So in this case it's min-max, this is what it refers to. So so this is theorem 1. For a fixed G, optimal discriminator is given like this. So P data is the real data and PG is the generative data with the new notation that we use. We could have used theta here also in our original notation, but it's okay. So this is the first result, okay? So we copy the loss function that we had before for the GAN loss, and this is what the GAN loss looks like. And so Z is from the known distribution and this is the real data. Now obviously, so so from above, for a given G, the discriminator D wants to maximize the VDG term, right? So we have used this compact notation VDG, which stands for these terms, right? Okay, so VGD, if we write this expectation in the integral form, then the first one is expectation with respect to P data. So that's why this guy P data shows up here and this log of dx shows up here. So we are kind of like expanding back, okay, again from going back to the integral. So here again, this is expectation with respect to the PG. So we are using this interchangeably, PG and okay. PG is like the generated one, okay. So I mean, if so a little bit of clarification is needed here, I guess. So if I take it with respect to the what is generated by the GZ, right? So GZ is trying to approximate some x. So we can call that as PDF of G, because Z is non-distribution, so that is PZ. But then G of Z is again some another distribution transformed by G, that we call it PG. Okay, so there is slight difference between PG and P. Okay, in American English, Z is also G. Okay, so but we can call it Indian one is PZ. Okay, so Z coming from PZ is standard normal, whereas after transform via G, and then we can replace GZ by X actually, and this X actually is the generated distribution. Okay. Okay, I guess we have to recall a few things. So for any AB in R2, the function y that goes to A log y plus B log 1 minus y. Okay, so this is looking very similar to what is there in the loss, right? We had the log and then log of 1 minus 6. So so achieves maximum in 0, 1 interval at A divided by A plus B. So again, this will be left as an exercise. This should be simple, I guess. So this achieves maximum. So this is seen as a function of y. Okay. So you see this as a function of y. So this is some function f of y where a and b are given to you. So what you have to prove is the maximum of this function f of y is achieved in the interval 0, 1 at a divided by a plus b. Okay, so this is calculus result. You know a little bit of optimizer right now. You take the gradient, equate to 0, and very likely one of the values will be the maxima. Okay. So actually it's done here, it seems. So f prime of y, we did the derivative and equated to 0, and indeed y came out to be, after solving, a divided by a plus b. It can be verified using second order derivative test that this is indeed the maxima. So second derivative test from we know, right? So we can take second derivative test, and since it's a maxima, so you have to say that the gradient is negative or positive, double derivative, because it's a maxima, right? So if it's a minima, then what do? The double derivative is positive, right? The rate of change of tangent is positive, then it has to be the minima. And if it's going like this from the top to bottom, then it's like the double derivative should be negative. So you have to actually do double derivative of f and then put this value, and it should come out to be negative, and then you say that this is maxima, right? Okay, so all these things could be done. We have done these things in our school also. So okay, so now we go back to our form. We could take y to be the dx, right? So we recall that loss for which involves d here, y could be seen as d of x, right? So we use that. So let y to be dx, then indeed the maxima of that for a given g, the maxima of that will be p data by p data plus pg, which is synonymous with a divided by a plus b. Okay, so and that's when this is maximum for a given g. So then the optimal discriminator will be now, so since it's optimal, we use star, which is a convention in the optimizer. So this refers to optimal d. It will be when will be of the form p data divided by p data plus pg. Okay, so this was our previous theorem. This was the theorem that we proved. Like this is the theorem we had. The optimal discriminator is like that. So we use this simple calculus result, and that seems to be okay for us. So now let us continue with that. So what next, right? So we copy that min max loss here, and so now with the optimal discriminator, so now we know for a given g what is the optimal discriminator, right? So we can substitute that d here, optimal d in place of d we will substitute d star, because we have calculated the form of that. So let us see what happens if we substitute d by d star. So if we do that, basically we are maxing out the d. I mean, by maxing out we mean that put the optimal d that maximizes the VGD. So that's where we put in place of d we have d star, in place of d we have d star, and d star g we know that it's p data by p data plus pg that we have identified. So this guy comes here and this guy comes here. Okay, so of g z is kind of like here it's given by x here. Okay, so these guys are split like this. So this is when I substituted the optimal discriminator, and okay, so this log4 guy is showing up, right? So the global minima of the virtual training criteria CG is achieved with if PG is P data. So what this now saying is that the global minima will be achieved because we have kind of solved for the maxima which refer to the discriminator. So we kind of got that form, and now we are still left with the minima problem, right? So what it's saying is that now the remaining part, which is the minima, that will be achieved if it is double f, right? So double f means if and only if. So it's like both ways, right? If PG is P data, then the minima is achieved, okay? And if minima is achieved, then necessarily PG is P data. It's necessary and sufficient condition, right? So and if that is the case, if that really happens, then at that point CG achieves the value of minus log 4. Okay, so we may go with the let us say we may go with the forward implications. Let's say, so let us say we start with PG is P data, okay, and then we will prove that that the minimum value achieved is minus log 4. Okay, so let us start with that. The D star is P data by P data plus PG. Let us put PG is equal to P data, right? So if we do that, then here we have PG P data. So P whatever you want to prefer in terms of G or data, it doesn't matter, but eventually either will cancel out and you have half, So now let us look into, so our D star comes out to be half. So let us put wherever we had D star to be half. So CG is expectation of log D star here, and then we have expectation log D star here. So we have log of half and then log of half here. For the both optimal case, the best possible D star could be half. So we just put half here as the best possible case, and then this turns out to be minus log 4. So that's the forward case. Now if we see the reverse case, so CG is minus log 4 is the best possible CG, and when it is achieved. Okay, so that's what we're trying to see here now. So we start with the CG, and so in the CG that was the form p data, and so basically this is D star and this is the D star, and we have done some tricks here to bring in the KL, obviously, right? So in the KL we needed this this kind of p data plus g divided by 2, right? So we did this adjustment of half and brought this 2 here just to make sure that it goes with nicely with the J's divergence, Jensen-Senen divergence, and this guy also goes well with the Jensen-Senen divergence. So we did that trick with the half, and this log half is taken out, and this is made into minus log 4, and the remaining term that you see here, this guy, and then this guy that you see here, this is exactly your KL divergence that you have. You have p data with p data plus pg, and you have pg with p data plus pg. This is exactly what J's divergence is. So we have minus log 4 plus J's divergence between p data and pg. Now for J's divergence we know that it's always positive, and 0 if and only if. So we know that for J's divergence is 0 if with the arguments are same. So for J's divergence to be 0, the arguments p data and pg must be same. You cannot do anything with the minus log 4, that's a constant, and you're trying to minimize this. So your CG is minimized when p data is pg, because that is when J's is minimized. So that proves our original argument that indeed the minimum is possible with because J's cannot go below 0. So J's minimum is achieved when p data is pg, and if it so happens, then indeed in that case we get CG to be minus log 4, which will become the global minimum. Okay, so as an additional thing, you may go back to the F divergence and see what happens there. So I leave this pointer for the moment for you to explore a bit later. Okay, so I don't know if I was fast or slow. Okay, so what we can do as a maybe we can wrap up then, and there is a slight extension to the GAN which is called conditional GAN. Idea is very simple. So now if you see DALI 2 or the recent one, then what happens is like you give a text, and then based on the text it generates the image, right? So that's like conditional. You from text to image, or so if your text changes, then the image changes, obviously. So can you do conditional generation? Okay, so based on some condition, it will generate something for you. So that was mentioned in the original GAN paper itself as a set of future things to do. And then after 6 months of publication of the original GAN paper, this conditional GAN paper came. And so the idea there was very simple. It's very simple that what you are going to condition on, let us say that is some level, okay? Some level you want to condition on. It could be text level, okay? So you also feed that basically, okay? And basically you append it, okay? So your real image is there, and you have some text embedding. You pass both to the generator and discriminator. So you can see from the arrow here, okay, so there is, okay, there it's showing, okay, sorry. Here it was not showing the generator block. So here, this is your real image, X eyes. This is your noise image, Z eyes. In the original GAN, this level and whatever this line that you see, you could remove. So that will be the original GAN. So only thing now changes is that now you have introduced the levels, the quote unquote conditions, okay? And now whatever condition it is, it depends. People are using it for quite a few things, okay? So in the abstract sense, level could be any condition that you want to put. And this, but important thing to note is that it should go to the generator as well as to the discriminator. Okay, so then it will try to generate images corresponding to the labels. So so this is essentially conditional GAN. So as I said, how it will go, it will just append it. Okay, so real image appended with the labels. You may have to change the input dimension of the discriminator to adjust for this this additional vector sizes, and also you have to do it for the generator, because label is also now appended with the noise vector. So So that's what it says, right? It can be extended for conditional model if both generator and discriminator are conditioned on some extra information y. Y could be any kind of auxiliary information such as class labels or data from other modalities. So you may be interested, maybe although it's handwritten digit, but maybe I want to do only 2. Okay, so that may act as a pointer that okay, just focus on the 2. Okay, generating the 2. We perform conditioning on by feeding y into both generator and discriminator as additional input layer. Okay, so that's what it's saying. So you may have this additional. You have input layer basically needs to be changed for both discriminator and generator. Okay, earlier it was only taking real and noise respectively, but now you have to change that. So all this is again in words. There is nothing new here. Okay, so in the generator prior noise, which is the standard normal random vector and y are combined in a joint hidden representation via some neural network and so on. Okay, so again, as I said, there is nothing new here. Yeah, so if you look at into the form, the way it is just that we change like this, right? So actually I forgot that conditional here also. Okay, I guess so. Okay, let me see. I guess I missed there also. Yeah, it should be x conditioned on y and basically z condition y. So that's how the min max just changes, that now you have the conditional generation rather than the usual generation, right? So that's what it means. Okay, so I guess yeah, that was all that I prepared for today. So that's all. Essentially this covers the GAN. We will move to WGAN. So for WGAN we will use, so here if you see the flow, here we started somehow with KL divergence and we extended a little bit to JS divergence, but JS divergence is a symmetric form of KL divergence. So essentially, although we started with F divergence and we specialized to KL divergence, but what we will do is that we will go to something called earth mover distance, which is another divergence measure. So we will. So what happens in certain class of generative model is which divergence measure you are starting with, okay, and how you are approximating by the lower bound. So in this case, we started essentially with KL divergence and Jensen-Shannon divergence, and we did some approximation on that via some lower bound. Now we will start with earth mover distance. So real p theta, and what happens if I use that? Then I get WGAN. But there again, we need some interesting tricks because again, earth mover distance is not easy to calculate. So then we need some ideas from optimal transport, how to have tractable algorithms. So we need some kind of regularizations and things like that. So that's fascinating area again. So that will be the topic of our next class. Okay, the WGAN. Okay then, thank you.